And as the chair has said, my name is Francisco Falcone. I come from the Pública University of Navarra in Spain. And I will be talking about some of the issues that we are trying to analyze in terms basically of wireless system operation applicable to a large density scenario, which can be the case of a smart city. So basically the outline of the talk is going to be a little bit of introduction and motivation. We'll talk a little bit about the simulation techniques and the scenario that we have implemented in order to test these results, the following results, and some concluding remarks. So I guess it has become more than apparent after the great two talks that we have previously had that there is an increasing amount of interest in what we can call context-aware scenarios. This means that we're going to have higher interaction, and this higher interaction is going to be given by different types of solutions, for example, augmented reality or distributed sensor systems. In any case, this can be applicable to many types of applications. For example, to home and building automation, we can be talking about ambient assisted living, e-health, or for example, more broader concepts like smart cities or smart regions. Now, this connectivity, in order to be capable of sensing and of trying to get some output out of this information, requires the massive adoption of some type of technology to transfer this. And basically, this technology is going to be dependent on wireless systems in a great deal. Now, this is the case due to the fact, as we all know, that there has been a massive adoption of mobile terminals and internet access to these mobile terminals. There's a very strong presence of wireless sensor networks and wireless local area networks, and of course emerging 4G and 5G networks, which is an extension of WLAN in any case. Now, further than that, there's also a social implication. It's the fact that there's new trends in the way that we also live, and we have new ways of interacting, and we have social networking, we have Web 2.0, Web 3.0, we have e-government, open government, and administration. So basically, all of this is giving rise to a scenario in which we have many, many new opportunities. And these opportunities are going to be appearing in the context of Internet of Things and the smart city paradigms. Now, if we go to one of the classical pictures, and this one has been taken from Tati and IBM, basically what we're talking about is that we're going to have multiple systems which are going to be interacting in order to provide a more efficient way in which you operate in cities. And this is going to require, in order to get these different systems, for example, energy management, waste management, transport management, citizenship management through open government, to take into account different types of elements. And one of the biggest ones is interoperability, make all of these systems operatable. Big data management, we saw the previous talks in which there is no way and you can get any information if there's no big data analytics in order to analyze this. We need seamless interactions from users, and very important, this does not have to be system-centric, it has to be user-centric. The user is going to be the main participant, the main stakeholder of the system. Now, in order to get all of this working, as I said previously, we need and we require wireless systems to get all this operating. Now, let me put you just one application which we have been working on, which is the concept of smart health, which is a little bit different than the concept of e-health or m-health. And in this case, what we're talking about is that we're sensorizing a city in order, for example, to obtain variables which are going to interact with different types of health elements. For example, they're going to interact with emergency services, but they're also going to interact with your local doctor in order, for example, to prescribe you the best possible way in which you can have a treatment, for example, if you have some sort of allergy in some sort of time period of the year. Now, in order to have this type of system in which, for example, a patient is going to be monitored 24 hours a day, multiple wireless systems are going to have to be interacting. And it's not only about the sensors, which play a key role in order to get the biophysical parameters, we need to transport these parameters. So we're going to have heterogeneous networks in which we are going to be interacting simultaneously, from a wireless body area network to a WLAN to a 4G system, for example, all working together in cooperation in order to get all of this working. Now, the aim of the work is that we want to analyze how these systems are going to work. And these systems, as we're going to see, are going to be strongly independent on interference, and therefore we want to see what is going to happen in a situation where we have complex scenarios in which propagation losses are going to be strongly dependent on the topology. how are these systems going to work? So therefore, what we're going to do is we're going to perform some simulations and some measurements of the scenario, and we're going to try to see how we can derive some results in terms of system-level analysis. Now, I know that this conference is not about radio propagation, so I'm going to keep it short. But the problem is I am a radio propagation guy, so sorry about that. If we want to analyze a complex wireless system in terms of the physical layer, we need to analyze the way in which radio waves are going to propagate. And we have very many amount of resources in order to do this. Now, we can go to very fast techniques in which we get analytical results, and this would be, for example, empirical based methods. They are very fast, but they are very dependent on the scenario, and therefore they have to be calibrated, and therefore the resolution is very low. On the other hand, we can go to full wave electromagnetic simulation, and they are very, very precise, but very extremely lengthy in time. It's impossible to input a city inside this type of simulation tool. So therefore, we have to go to other techniques which combine the best of both worlds, and in this case, we would be talking about deterministic-based code, which the main player here would be ray tracing or ray launching code. And this is basically what we have done in our group. We have implemented an in-house 3D ray launching algorithm, which is going to take into account all of the physical parameters, basically topology, which means what is the way in which the structure is implemented, how are the walls, how are the ceilings, even how are the trees if we have to implement trees, and of course the material parameters in terms of frequency dependence. So this is going to be the initial scenario. We're going to take a typical city, and in this typical city, what we're going to do is that we're going to implement buildings. These buildings are not going to be just the facade of the buildings. We're going to have the complete indoor structure of these buildings. They're going to have ceilings, they're going to have doors, they're going to have windows, they're going to have everything. And we're going to put transmitters and receivers along this type of scenario. So once we do this, the typical results, which we will extend to some applications, as I will show you towards the end, are going to be the following. The first thing that we're going to do, we're just going to estimate path loss, and path loss is going to be a critical parameter, because from that we're going to relate that to sensitivity, and from that we're going to relate to coverage, and from that to system level performance. So here you can see what are the parameters that we have employed. We have considered a conventional 2.4 gigahertz scenario, but this can be extendable really to any frequency. And typical transmit powers that we would be using, for example, in a Wi-Fi system or in a high-capacity Zigbee network. So here we can see some of the results that we're going to be obtaining as a function of what we're going to have if we place a transmitter in this scenario, and therefore what is going to be the propagation losses in terms of distance. What is going to happen is that we have a very well-known variability, which is due to multipath propagation. And this is basically what is going to determine that it's not as simple as just saying that we lose power with distance, but we really must consider the impact of topology inside of the scenario to adequately place those sensors that are going to retrieve whatever type of parameter we need to transmit. If we analyze this in terms of transmit power, for example, if we take a typical Zigbee mode, which is going to be one of the main drivers for wireless sensor network deployment, we have different types of operation in terms of transmit power, which is going to impact directly on energy consumption. And as you can see, we can see the X scale is the distance. And of course, if we increase power, we're going to have a notable increase in the distance, but also we're going to have a notable increase in power consumption, as we will see. And again, this can be applicable if we just change the position of the nodes. In this case, this would be a gateway that would be placed on the roof of the building instead of on the floor level. And as you can see, again, our consideration of propagation losses change quite a bit. If we change frequency, we're going to have simply a shift in what would be the propagation losses. And this is a very well-known phenomenon, which is given by the fact that we increase wavelength, then propagation losses are going to diminish. Now, the case that we have all this variability is given by the fact that we have so many interactions with the environment. And this can be clearly seen in the case of taking into account time domain parameters, and this would be the result of obtaining a power delay profile for two different scenarios inside the simulation setup. And as you can see, we have many components versus time. And this is given by the fact that there's many, many reflections and interactions with the environment. This is the physical description of what is going on inside. Actually, if instead of taking one exact point, what we do is that we take the full two-dimensional plane, for example, we can see the variability in what would be the distribution of delay inside of the scenario. And as you can see, it's strongly changing inside of the scenario. And again, this is a natural conclusion that can be derived from the fact that we have very strong interaction with with the elements inside of the scenario. Now, in order to get a little bit more insight, what happens if we put an active access point, for example? You can consider this as an access point of a gateway of 802.11 system, and all the sensors are going to be interfacing with that access point. Well, what we're trying to depict here is received power levels as a function of distance. The whole 3D volume has been simulated, but in order to get a little bit of insight of what's going on, only certain planes have been depicted. Now, as you can see, as we start moving the position of the locations of potential receivers, the configuration of received power changes, and it changes in a non-linear way. I mean, it changes very, very dependent on what is going to be the elements inside the scenario. The same can be applied on a horizontal plane, which is more simpler to see, and as you can see, the distribution can be depicted for the whole scenario. It's also interesting to note that the fact that we have buildings and we have walls does not mean that the signals are not going to be propagating inside of these scenarios. And this is very important because it's not only the fact of considering what is the coverage of our system, it's also the fact of considering what's the overall interference of our system. So we must perform this type of analysis with a complete population of the scenario in order to consider overall degradation by interference from other users and therefore impact on how we must design our network in terms of the number of nodes depending on the system that we must place. And this is going to be very critical, for example, in 4G femtocell and 5G femtocell deployment. Now, another element that we can derive, which is very interesting, is that we can do an estimation of what is going to be in the overall scenario, the power consumption levels that we would require of potential receivers that would be placed inside the scenario if we modified the location of potential transmitters inside the same scenario. Now, as you can see, the distribution is homogeneous, but we do have locations where it would not be interesting to place these transmitters due to the fact that we would obtain higher levels of required current that would be operating the potential receivers. And those are the peaks that you can see on the different points of the image. Of course, this also is related with what is going to be the performance in terms of coverage capacity ratio. We're very used to seeing that we need to receive a certain amount of signal in order to get the system working. But this amount of signal that we must receive is strongly dependent on what is the modulation scheme that we have, and therefore also on the speed of our transmitting links. Now, this must be taken into account because maybe we have designed initially our system to be working at a speed of 256 kilobits per second, for example, which could be a max speed for Zigbee. But in the end, if you start increasing interference, or if you require to increase transmission speed, then probably your coverage radius is not going to be adequate, and therefore you're going to have to redesign the network. And it's probably better to do this before deploying the network. So here are some other examples on real indoor scenarios. Here you can see, for example, a coverage plot of a signal-to-noise ratio in a scenario. This is a conventional indoor scenario in our university, which has relative complexity and has a relatively large amount of sensors inside. It has 8 sensors in total. And as you can see, you can deploy what will be the signal-to-noise ratio maps. And this must be taken into account. It's a non-homogeneous distribution, and therefore, we must analyze what would be the best way of locating this network, because this network is not optimized. This is a non-optimized network, and we must use this information in order to see what would be the best way possible to make this network work. Of course, we can also use this in order, for example, to take the decisions in the ways in which we want these networks to operate. And for example, if we want to have very efficient in terms of energy consumption networks, probably we're going to use aggregation schemes and clustering schemes in the wireless sensor networks, and we must know what type of clustering algorithm we must use in order to aggregate the data and send this data to the gateway. So here we can see some examples in which, depending on the way we aggregate these nodes, there's 2 examples, zone distribution and a cluster chain distribution. Signal-to-noise ratio maps can change, and therefore the quality of our network changes, and therefore the performance of the network is also going to be modified. As another example, if, for example, we take into account what would be the overall interference levels of the system by increasing interference, for example, because we have more users or we have intra-system and inter-system interference from our own system and also from collateral systems, for example, Bluetooths and Wi-Fi's that would be blocking, for example, a Zigbee operation, then what we're going to have is different types of coverage maps, different types of distributions of power that we must imply in order to get operation of the overall network. And again, we can have a distribution of transceiver current consumption and therefore analyze what will be the best possible topological location of the sensors inside of this very simple scenario. It's relatively big, but it's relatively simple. Now, another case, in the case of a smart city context, would be an urban outdoor. And this is, for example, work that we're doing in our university. It's a very simple thing. Well, we have trees, we have located wireless sensor networks outside, and we want this wireless sensor network, which is based on Zigbee ad hoc network, we want it to interact with the users. We will see what application we can find. It could be social networking. It can be just for transmitting information from one another. It can be for security purposes. And the fact is that we must analyze what is the best possible way in which we must implement this network. And therefore, we must also take into account topomorphological issues, for example, in relation to how trees are going to interact with radio waves. They're going to be natural scatterers, and therefore this has to be modeled as well. And here you can see, for example, what is going to be, again, the power consumption that we're going to have in terms of current, and what are the deployment stages as a function of the speed in which we want our network to operate, and therefore the amount of cells that we need there. So, just to give you some conclusions, well, in the case of any type of wireless system, topomorphological considerations play a key role in order to get things working. Now, these modifications in the way in which our sensor network has to be deployed as a function of what type of specific data we need for what type of application we want to implement is really going to imply big changes in the way RF power is going to be distributed, let's say the useful as well as the interfering power. And therefore, this is going to really require thorough analysis in order to optimize the way we're going to deploy a network that is going to be huge in the amount of elements that we're going to have, because we're going to have, due to IPv6 and IoT, many, many nodes potentially connected, and many of them are going to be wireless. And therefore, we're going to have a true headnet operation. And this headnet operation is going to make intensive, very intensive use of the spectrum. So basically, what we can foresee humbly is that we're going to have a context-aware scenario with Internet of Things, smart city, context-aware, and it's going to be a really, really big and interesting challenge to face. So that was all. Thank you so much for your attention.